All right, today we're taking a tour through one of the most fascinating and diverse neighborhoods on the entire periodic table, the P block. Now, this is the only place where you'll find metals, nonmetals, and metalloids all living side by side. It's a source of pretty much everything, from the carbon that makes up life itself to the silicone that powers your phone. So let's dive in. So here's our roadmap for the tour. First, we'll get a feel for what makes the P block so incredibly unique. Then, we'll unpack the fundamental rules that dictate how everything behaves here. After that, we're going to investigate a really crucial exception to those rules, something that explains the weird chemistry of the heavy elements. Then we'll take a quick tour of a few key groups, get to know their personalities, and finally, we'll wrap it all up with a concise summary that's perfect for getting you ready for your exams. So, what's the big deal with the P block? Well, in one word, diversity. This isn't some uniform block of elements that all look and act the same. No. This is a true chemical melting pot, and that's exactly where all its power and importance comes from. I mean, just look at this incredible range. It's what totally sets the P block apart. This is where you find the nonmetals that are the absolute building blocks of life. Carbon, oxygen, nitrogen. It's also home to metalloids like silicon that literally power our entire digital world. And of course, you've got common everyday metals like aluminum. No other block on the periodic table has this complete set, and that's why its chemistry is just so endlessly rich and important. Okay, so to make sense of all this diversity, we need to understand the underlying rules. Think of these as the fundamental laws of the land that govern how every single element in the P block behaves. And you know what? It all comes down to this one little line of text right here. Their electronic configuration. P block elements are defined by the filling of their outermost p orbitals, starting with just one electron in group 13 and going all the way to a full, stable set of 6 in the noble gases. This ns² np1 to 6 structure is the fundamental blueprint, the DNA, really, for their entire chemical identity. But here's where it gets really interesting. There's this fascinating quirk where the first element in each group, think carbon or nitrogen, behaves totally differently from the rest of its family. Why? Well, it's for two main reasons. They are uniquely tiny, and they don't have any d orbitals they can use. Their small size lets them form incredibly strong double and triple bonds, which is the secret to the stability of all organic chemistry. Now, their heavier siblings, they can't form these bonds nearly as well, but they have a different trick up their sleeve. They can use their available d orbitals to make more than 4 bonds, something we call expanding their octet. And of course, we have our trusty map for navigating this whole landscape, the good old periodic trends. As we move down any group, the atoms get bigger and more metallic. Simple enough? And as we move from left to right across a period, they get smaller and hold onto their electrons much, much tighter. That means it takes more energy to rip one off, that's higher ionization energy, and they pull way more strongly on electrons in a bond, and that's higher electronegativity. But chemistry just loves its exceptions, and the P block has a huge one. It's called the inert pair effect. And it is absolutely essential if you want to understand the unique behavior of those heavy elements sitting at the bottom of the block. This one's a game changer. Let's frame this with a classic chemistry puzzle. Carbon and lead are in the same group, group 14. They both have 4 valence electrons. So why on earth is lead perfectly happy just using 2 of them to form a +2 ion, while carbon almost always uses all 4? The answer, my friends, is the inert pair effect. So the effect actually starts deep inside the atom. As we go down the periodic table into the lower periods, we have to start filling up these inner d and f orbitals. Now, these orbitals are really diffuse and spread out, which means they do a terrible job of shielding the outer electrons from the massive positive pull of the nucleus. It's like trying to block a hurricane with a piece of paper. It just doesn't work. Okay, let's break this down step by step. First, the nuclear charge, the number of protons, gets way, way bigger as we go down the table. Second, as we just said, those inner d and f electrons are terrible shielders. So what's the consequence? The outermost s electrons feel a much stronger pull from the nucleus than we'd expect. And that means it takes a huge amount of energy to pull them away and get them involved in any kind of bonding. For a heavy element like lead, the energy cost to unpair and use those 2 s electrons is often just too high. Think of it like a business decision. The energy you'd get back from forming 2 extra bonds simply doesn't justify the initial investment. So that pair of s electrons often just stays put, remaining chemically inert. And this is what leads to the element showing a stable oxidation state that is 2 less than its group number. All right, now that we've got the rules and the major exception down, let's see how this all plays out in the real world. We'll take a quick tour through a few of the groups to explore their unique chemical personalities. First up, group 13. These elements, like boron and aluminum, are defined by one thing. They are electron deficient. See, with only 3 valence electrons, they have a vacant p orbital, even after they form 3 bonds. This makes them absolutely hungry for an electron pair, which is the literal definition of a Lewis acid, an electron pair acceptor. So how do they solve this problem of being electron deficient? Well, they get clever, really clever. Instead of just existing as simple single molecules, they often team up to form what we call dimers, like the diborane and aluminum chloride you see here. They come up with these exotic ways to share electrons over multiple atoms, forming these bizarre 3-center, 2-electron bonds, all in a desperate attempt to get a stable electron configuration. Okay, moving next door to group 14, we run into a really famous property, catenation. That's just the ability of an element to form long chains with itself. But here's the question. Why is carbon the undisputed king of this, forming the complex backbone of all life as we know it, while silicon's chains are way less stable and form the rigid backbone of technology instead? And the answer is staring us right in the face in this table. It's all about bond energy. The carbon-carbon single bond is exceptionally strong and stable. It's this strength that allows carbon to form the vast, complex, and stable molecules that life requires. But as you go down the group to silicon, germanium, and tin, look what happens. That bond energy drops off significantly. The bonds just get weaker, and the ability to form long, stable chains pretty much disappears. Our last stop on this quick tour is group 15, which is known for its incredible chemical flexibility. With 5 valence electrons, these elements can show a massive range of oxidation states, which is really just our way of keeping track of an atom's electrons in a compound. And nitrogen is the absolute master of this chemical versatility, showing every single oxidation state from -3 all the way to +5. This is what allows for the rich and diverse chemistry of everything from fertilizers to explosives. All right, we have covered a lot of ground, so let's bring it all home and condense the most important concepts into a single exam-focused summary. This is your revision cheat sheet. This table really ties it all together beautifully. Each group has its defining feature, right? Group 13 is electron deficient, Group 14 is the master of catenation, and hey, this table also includes Group 16, the chalcogens. Think of oxygen and sulfur. They're masters at grabbing 2 electrons, forming the oxides and sulfides that are essential for minerals and for life. But look closely at that oxidation states column. You can literally see the inert pair effect at work. Thallium prefers +1, lead prefers +2, and bismuth prefers +3. Every single one is 2 less than their group's maximum. It's all connected. And we'll end on a forward-looking thought. We've seen how these fundamental principles, like shielding and nuclear charge, dictate the chemistry of all the p-block elements we know and love. So how could we use these exact same rules to predict the properties and stability of the super heavy elements in the next row of the periodic table, elements that humanity has not even created yet? It just goes to show that understanding these patterns isn't just about passing an exam, it's about mapping the future of chemistry itself.